Hello, January 20th, 2024. We begin as we continue with moments in motion to try to understand a little bit today how it can be so that a usual sort of discourse kind of follows a common canon of a culture that has when we reflect on Zeno's paradoxes of motion, that they are not, that they are actually exercises in deductive inference to arrive at why an infinitude of events in time occurs in sequence, which carries all such matters of the course of passage through the space we inhabit in the time that there is. So when I left off last time, as I was mentioning, I don't really have a great facility converting between Celsius and Fahrenheit. So when I said, 30 was too hot and 40 was bad, that actually it's kind of like, well, 30 is plenty warm, that 40 is too hot and 50 is what's inhospitable. So today, what I thought to do was that the studies that we've been having in this talks recently have been about waves, largely about waves. Wave is really the common milieu, waves and energy, in terms of the discreteness elementarily of the quantum mechanics, while that the aggregates are always only in bulk for the running constants in current, and that the study of the quantum mechanics is a very carefully defined continuum mechanics with the conceit of the particle, the concession to that. It's a model of how we can approach these things with our classical mechanics and the milieu of the calculable and the way these things go. So in the past few days then, in accordance with that, is that, it had been cold enough to be freezing, but the temperature's gone up by like 30 or 40 degrees within a day or two. Fahrenheit. All right then. With that kind of introduction, what else I've been trying to figure out over the past few days is just usual reverie. I don't plan these talks. I don't really make too much an effort to sketch out ahead of time what would be kind of the considerations. But one thing I've been looking at for a long time is this book, and it's I got it today. So this is what I acquired today, and we'll be looking at it, and it's kind of in the same context as waves and layered media and the sonar and radar and stuff like this. And this book is from a symposium in 1969 or 1970. And it's kind of interesting how science is in mathematics and science, because it's kind of important that mathematics is always ahead of science in ways, so that science has the mathematics to make the models of its things. But then for a while, and for quite a while it's been this way, is that physics kind of got ahead of mathematics. And so the physics of things with regards to technology and its applications really had that a lot of the different ways that these things were developed were as of the empirical vis-a-vis the theoretical, and it's so. And so whether that's the theory of electricity or even mechanics or all such sorts notions of the behavior of the molecular and in biology and these kinds of things, vis-a-vis the central dogma of molecular biology, and as with regards to the genetic machinery, the genome with respect to the bacteriome, as of after the proteome and the viriome, all one thing, kind of a viriome, is that the empirical has kind of led the way, and trial and error was the sort of thing that was brought about many of the great advances, while at the same time the theoretical, of course, is key. We must have a common concept and an understanding of theory to make things as well defined in this way. So one of the stories that's often told in this kind of environmental milieu is about the flight of bumblebees. So the flight of bumblebees is a variety of things. One is kind of fugue. It's kind of a musical progression of notes in the chromatic that rise and fall and rise and fall, and it's the flight of the bumblebee. But the flight of the bumblebee refers to study after the mechanics of flight and the study of bumblebees and their flight. And according to the theory and the study of the bumblebees and the flight, is that the theory arrived at a derivation showing that it was theoretically impossible for bumblebees to achieve flight. Yet they do. You know, this is one of those things, kind of like when, they discovered circulation of blood in the 1850s. 1850 BC is more like it, you know, but, or when, you know, when the old wrapped is new. Old wrapped is new is always a thing. Or here there's like anything that reached 60 miles an hour would explode, or anything that reaches the speed of sound would explode. These being basically as built up after the natural units and the limits and the theoretical, and how it arrives at that, yes, those are pretty strong limits vis-a-vis the theory is bounded by its assumptions. In this case, they were wrong. And so the flight of the bumblebee is something to figure out. So one thing that has been always kind of an interest is the study of the mechanics of flight. And it's basically aeronautical as flight in an aerial medium, and astronautical as flight as of a vacuum of space. And then there's also, with regards to travel through such a medium, is that the aqueous or submarine or underwater is also kind of considered the same way. And so there's this usual idea that there's lift and drag. And so according to an aerofoil, usually, is that there's a balance of lift and drag, that the usual objects have drag and not lift, and aerofoils have lift besides drag. And then this is the notion of the Bernoulli principle, which is really kind of related to the Venturi principle, where the Venturi principle is that compressed air will make a cooling effect or a heating effect. And the Bernoulli principle is kind of the idea that according to the shape of an airfoil, the faster passage of air over the top of the foil results a lower pressure, that there results cumulative lift. So this is kind of the idea of, for flying machines and such, the theory. And kind of the descriptive elements and the causal elements, the explanatory factors, these being the kinds of things which so regards to these things. So I've been looking at this book for a while, and I'm pretty excited about it. It's called Boeing's Symposium on Turbulence. And it's from 1969 from Cambridge Press. And what it is the proceedings of a symposium. So when we talked, when there was talk a little bit about how, you know, sometimes science is in front of application, and when there's conferences and colloquia, when they're the get-togethers of academic forefront types, then we call these, you know, symposiums or conferences or colloquia, basically in an order from, you know, the World Symposium to forums of any sort, get-togethers. And so this says what it is, and I haven't really looked at this yet because I just got it, but it's reprinted from the Journal of Fluid Mechanics. So volume 41 of the Journal of Fluid Mechanics, this is pages 1 through 480 of it. So I don't really have a copy of the Journal of Fluid Mechanics sitting around, but it's really pretty amazing that these days that most research university libraries would either have one around or have access to same. So this is not something that's inaccessible then, but this is kind of the unique imprint of it. Cambridge at the University Press. Now it's not just Cambridge University Press, it's Cambridge at the University Press. Held at Seattle, Washington, USA, 23 through the 27th of June, 1969. And so what this is published by the Syndics of the Cambridge University Press, out of London and New York, and this was printed in Great Britain at the University Printing House in Cambridge. So it's a symposium on turbulence. So when we think about turbulence, you might recall some previous talks when we were talking about the vorticial, the wash, the fluid wash, the model of vis-a-vis fluid is in flow and flux, and of the wash and the vorticial, the turbulential, the turbid and the turbulent. Then here is with regards to there's stuff like Navier-Stokes millennium problem, or really there was a lot that went into the Fourier-style analysis called the heat equation. And these days there's a lot going on with that, because these theories have great working linear models for very careful assumptions, which don't always hold. And so there really is room for a lot of different kinds of approaches that result either applications for particular other assumptions or more general theoretical things overall. So for the Fourier-style analysis, which is originally the study of things like the conduction of heat through a uniform sphere made of brass, or the conduction of heat through a wire, then as we talked about here, there's things going on with the Dirichlet problem and equipartitioning and the one-way nature or the gradient, and as with regards to whether that's always a seesaw or teeter-totter with regards to its overall tendency, and the tendencies and propensities. And then, so heat and heat for thermal first law and thermal second law. And then there's also, these days they're studying, they're like, wow, heating and cooling are kind of two different things. And so it's kind of like when we were talking about the difference between the central limit theorem and a uniformization limit theorem. It's like all the science is kind of built up one way, and it works great all the way out to the horizon, which is the horizon of a flat Earth, And so trying to figure out how the great circles come back around really is still kind of a thing. The other day or today, I was talking with somebody, and we were talking about physics and theories of cosmology. And one interesting point was like, well, that both the Big Bang theory, that the universe started from a point and became a thing, and the steady state theory, that the universe is eternal and has always existed, both of them fit the data somehow. This is just an example of this combined milieu of this theory of some potentials in universals and in the eternal, what that means. This can be shrunk to a much, 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 much smaller box just called the square of opposition and establishment of a dialectic and looking at things from both sides. So in this book, it has a combination of theory and experiment. So it describes turbulence functions and shear flow. So we talk about stress and strain and shear and the transverse and forces and coupling vis-a-vis nonlinear electrical mechanical effects and applications, and the tensors, which reflect upon forces and couplings of stress and strain, and here with respect to shear, and those representing interfaces as about what happens when there's the highly dynamic at the boundaries. So winding that forward up to last talk, then that's just as of up to the continuum boundaries and whether it reflects symmetry and variance and symmetry flex, and as with regards to these things. So shear is a pretty, as you can imagine, it's a highly nonlinear aspects of conditions associated with flow, and specifically rapid changes in flow, or rapid changes in with regards to the difference between like a balloon with a pinhole that slowly deflates or a balloon with a pinhole that explodes. These are just kind of examples of either side of the singularity of the events with regards to what's called chaos theory, but really with regards to what's called dynamical modeling about our differential systems and about the initial value problems and boundary value problems, and what happens when a small change at the initial conditions results large changes in the overall result. With the overall quite all the same tendencies, just as a matter of tendency 1 and tendency 2, and whether or not they just kind of go out exponentially, or one or the other falls off, and the other one results asymptotic. Large-scale motion in the intermittent region of a turbulent boundary layer. So this gets a lot into the same things as we've been talking about in the waves and layered media. These are the layers. And so sometimes layers are, as of sharing their motion together, and other times layers reflect like an air wall or something like that. Distinct layers and layers with entirely opposite signs of their conditions of flow and flux in them that still happen to be neighboring as regards to what's called transition layer. That transition layer is this idea that, well, in our theory we just have boundaries, but anything that crosses a boundary goes through a transition, and that's how it is. The two-dimensional mixing region. So, transition, mix, analytical theories of turbulence, relationship between a Wiener-Hermite expansion and an energy cascade. So a cascade usually reflects either just tumbling together or criticality. Turbulent dynamo action at low magnetic Reynolds number. Now the Reynolds number is something we looked at quite a while ago, and the Reynolds number is an empirical descriptive value, and it gets into the qualitative and the descriptive and the quantitative as of the empirical. So Reynolds number is something you'll find a lot in fluid mechanics and these kinds of things, with regards to what's yet today largely governed in theory by this empirical. A numerical study of three-dimensional turbulent channel flow at large Reynolds numbers. So in the highly nonlinear, the dynamic, the extreme, these are notions of when otherwise the classical solutions break down, but they still just go. They're still the same thing. Then with regards to and mathematics has to accommodate that. For that would point to something like the superclassical, superfluid models and this kind of thing. So anyways, one of these papers is The Mechanics of an Organized Wave in Turbulent Shear Flows by AKMF Hussein and W.C. Reynolds, Reynolds. So I suppose that'd be a good place to start, because that's what I really am interested in, is what are the formalisms of this waves and layered media's behavior. Milyan-Chikov's 1939 hypothesis for 4-point time correlations. This is part of multi-point time correlations in grid turbulence. So grid, when you think of grid, you might think of it as finite element analysis, whereas we don't really have a continuum analysis, but we can break it down into grids. And then as that gets smaller and smaller, it gets more refined. And then there's still always the conditions at the edge, or as with regards to discontinuities out of it. But it's the same kind of thing as quantum mechanics is overall. Finite element analysis. As after the empirical, observational, measured constants, running constants, fundamental laws of physics. W.C. Meacham's equilibrium characteristics of nearly normal turbulence. So nearly normal, you might think on the one hand is they go together, but normal usually just means orthogonals, at right angles, at odds, where mostly natural words in physics and mathematics kind of mean the usual things, but there are other things, and those are the usual things. we discussed some consequences of assuming that two different nonlinear model equations and real turbulence are nearly Gaussian. So that's about analyticity, and so Gaussian is going to be explained by this complex analysis of the Eulerian and Gaussian, and then he's up to it's kind of cool because it's before bracket. He's just got it into brackets, and he represents it about the Dirac delta, about Cameron-Martin-Wiener functionals. The functionals provide a useful representation for nearly Gaussian processes. The use of these functionals in the examination of nonlinear stochastic problems is presented more fully elsewhere. See Wiener, 1958, Cameron and Martin, 1947, Imamura, Meacham, and Siegel, 1965. It will be useful, however, to review some of the salient characteristics of such expansions here. The singular set of functions. Since A is Gaussian, U will be Gaussian. You see that the H are symmetric. So Gaussian is going to reflect a couple different things. One is for the Gaussian distribution and the central limit theorem, the stochastic, and then the other as with the Eulerian complex. And its real parts that result its utility. In most practical problems involving turbulence, one is faced with statistically inhomogeneous turbulence, which is frequently driven as approximately in statistical equilibrium. So the statistical ensemble is one of the great things is about how gas laws and that are derived point to the existence of turbulence in the lower atmosphere, which is driven by wind shear in that region. Another important application lies in problems involving turbulent wakes. In such applications, we find the turbulence driven by large eddies which couple into the mean shear flow and derive their energy from that flow. So here this is pretty great because it kind of relates everything in one fluid model or one gas model, and with regards to flow, and here with flux, and in this kind of context, we already have available these concepts of regular models and whatever alternates in terms of the tendencies and propensities of flow, so associated conditions at boundaries, and their opposites where they're reversed in natural units, and as of about 1, 0, and infinity. 1, 0, and infinity here are the three only numbers that really kind of get started the whole thing. Numbers, 0, 1, and infinity. 1 is a natural unit. We shall here replace the large-scale energy sources by an equivalent forcing term both in model and real turbulence. So this is in terms of approximations and error terms. Every numerical method has is an approximation. That's why they call it numerical methods. And some are exact, and then we would call it closed form. But otherwise, a numerical method is an approximation, and so it's close, hopefully, and modeling the error term is reducing it as much as possible. Then that there's placement for that in the stochastic for measurement uncertainty. And then there's placement for that, like with regards to motion and here turbulence, with regards to these things, that otherwise approximations are not closed forms, but they're everywhere in the applied, vis-a-vis. Modeling the error terms, and then according to the products of approximations, maintaining those as quantities, then just what results scientific numbers, which have as maximum of their precision, the maximum of their precision, the factors. So this is getting into stationary driven turbulence. So it just helps to reflect like how a vortex starts, and how a curl starts vis-a-vis an interface or shear, where this is where when trying to figure out how something in motion will have according to its initial conditions left or right branching, This also is like, well, when you force a surface flow against something with a point, it will split. So, how so? So equilibrium characteristics, stationary driven Berger's model turbulence. Berger's model will be treated here in a way analogous to that used in section 4 for the incompressible Navier-Stokes equation. The transform used is time again implicit. U of k equals integral from negative infinity to infinity of e to the ikx ux dx. So, and the same for the forcing term. The Berger's equation is the partials of u. Well, actually, it's the partial of u with respect to t and plus u times du dx. So it's a substitution of variables. Equals v second partial u in x plus fx. With the transform, u dot k equals negative this quantity I, k over 4 pi, which will be kind of familiar with the terms as of these wave equations and the same models of the wave functions and the Gaussian Eulerian analysis. And then after the substitution in terms and integrating by terms and this kind of thing. And excuse me if my usage here is a little bit loose because it's meant to be descriptive in a sense while still accurate. UK prime, UK minus K prime, so as of before and after their product, they come together that way. That times dk prime minus v k squared u okay plus f of k. The energy equation is constructed as before with analogous definitions of the triple velocity correlation. Numerical experiments show that when the forcing term is Gaussian, even moments are related as for a Gaussian process. In figure 2, the results of such an experiment are shown. We obtained from the 0/4 cumulant, sometimes called quasi-normal approximation, and he's got a breakout in terms of after down from the second partials and their squares, what is as of for Rolle's theorem and L'Hopital's rule, in these rank ordering or rank lowering types of approaches. And, given that k plus k prime plus k double prime equals 0, so as when only the higher order moments of the acceleration are kind of in it, and are non-zero, or not necessarily zero. Here, though those are the only terms in this down to the second partials. There's a lot of background in these previous talks, and so with regards to the Laplacian and the second order derivative, or is it with respect to acceleration and the linear moments and force equals mass times acceleration, vis-a-vis all the higher orders of acceleration and the stop derivative and these kinds of things, is for reflecting on then how these numerical methods and these approximations have a lot going on and where otherwise the nonlinear terms might exist. And in fact that it's affected that the natural relation is in of those. See, this next section is Craigna's convergence to turbulence functions. The principal tool is a technique for expanding the Fourier transform of the unknown function by use of a set of orthonormal functions. Fourier-style. Application of the Lagrangian velocity correlation and the eddy diffusivity for marked particles in a three-dimensional random velocity field yields results that agree excellently with computer simulations. The approximation procedure is extended to expansions in strength parameters, e.g. Reynolds number expansion, and to an expansion about the direct interaction approximation. The latter is based on a new model representation of the direct interaction approximation. An implication of the work is that the usual diagram expansions obtained through term-by-term averaging over a Gaussian distribution may not uniquely determine the functions they represent. It may be that truly meaningful expansions are possible in general only for distributions which bound the amplitudes in individual realizations. Suppose that an initial ensemble of turbulent velocity fields is specified by all its moments. Moments. It's moment in motion. This is relevant to this talk. Turbulence theory is the name of this talk. Then straightforward manipulations of the equations of motion yield formal expansions for any desired statistical function in the form of Taylor series in time or in the form of power series in a strength parameter associated with the nonlinear terms in the equations of motion. This is from Bachelor, 1953, Creighton, 1966. In addition, several less elementary formal expansion schemes for turbulence have been proposed in recent years based either on rearrangements of the Taylor and strength parameter expansions by Wild, W-Y-L-D, 1961, Creighton, 1961, Lee, 1965, Orshag, 1966, or on expansion about an assumed approximate statistical state. Edwards, 1964, Herring, 1965, 1966, Edwards, McComb, 1969, Phythian, 1969. The present author Creighton pointed out that any of them very likely has a zero radiance and convergence in the relative parameter, while even if the radiance of convergence were infinite, in practically many terms might have to be summed to get valid approximations to statistical functions from truncations of the series. So, limits. Moreover, the complete expansions contain insufficient information to determine the statistical functions. So this is where we want to kind of, like these days they talk about the Gaussian central limit theorem, and they say, well, how about we just let it slide a little bit and we'll call it lognormal analysis, and we have a different sort of limit theorem in that still keeps related the median and mode and the upper and lower 5%. It's like, okay, that's great. You know, I mean, you've opened up an entirely new realm of analytical capacity and taken a whole class of error cases and made it so that you can check both sides and see that one of them doesn't work out. But it's still not quite the long tail or the error record or this uniformization limit theorem, which, as of matters of random chance, is basically this kind of combined model. Big bang or steady state. Central sample or uniform sample. It's both. Generally, it's one or the other. Just keep things simple because it gets involved in a huge stack of these things. This is how it's going. Is that in recent years it's like, well, we'll just use lognormal. Yeah. Moreover, the complete expansions contain insufficient information to determine the statistical functions uniquely in the absence of additional sources of information about analyticity properties. So also in the Gaussian, when it's trying to figure out, well, where do these wave numbers land? It's like, well, we're just using the Gaussian. It kind of treats it as if after this model of reflections and rotations, as long as it doesn't hit a lock, and when it doesn't, then it's up to a function. So we're looking here for Reynolds' paper, and it's somewhere further down the road. And so the developments in here are in the Gaussian Eulerian, in the formula of polynomials and powers, ranks and powers, and roots and powers, the integrals and the higher order integrals about an analytic, a region of analysis, the regions of analysis. With regards to the absolute, this is a squaring and boxing, and this x squared plus minus 1, the hyperbolic cosine and the hyperbolic trigonometric, and are really going to have to look at that a little bit more with regards to the utility of the function of it, and why it doesn't really so apply as for the orthogonal functions, but how it does kind of carry back out to conics and this kind of stuff. Whereas the conic sections is the usual model of ellipses, parabola, and circles, and with regards to that the hyperbola is it's a particular model of 90 degrees that nowhere is a right angle. Outside the box. Thinking outside the box. The inside of the box is already very well filled in. Exponential fall off. Ooh. The converse is not always true. The following three statements express sufficient conditions for convergence. Here it's kind of necessary to combine and roll up not only all the convergence tests, but all the divergence tests. And then with regards to the telescoping and quantities, those also have to be kept because the bookkeeping is necessary in the quantities because they're not absent their derivations. So that's just the usual thing about these things. $241 is where we're going here. Consider the function satisfies boundedness, orthogonal expansion, convergence, illustrations of the expansion method, some diagrams. These are very cool. Shape and scale parameters, weightings, best fitting sums of Gaussian curves, approximations, statistical methods, cosine transform. As it happens, this, which is about the simplest with the correct qualitative behavior at large T, is related to Gaussian weight by an integration over a width parameter that precisely corresponds to the P integration in 3.4. After the Fourier-style analysis, there's much to be made for the L'Hopital's rule, Rolle's theorem, and the Taylor-style analysis, or Maclaurin-style analysis, because it's basically separated as about the trigonometric analysis in the infinite series and the powers in geometric series in the infinite series. So together those two kind of have to be, and it's something to be said for having a combined style analysis with regards to the power terms and the periodic terms, because one might imagine is that you can just kind of put those on either sides and then sketch those out in the middle, and then what falls in the middle would be an appropriate middling term for otherwise this middle of nowhere. That's my new latest idea. A three-dimensional diffusion problem. Convergence to turbulence functions. This is a good word. Approximants. Normal distribution. Gaussian distribution. The diffusion problems, and here that's in terms of the tendency of things to diffuse in the dissipative and attenuative, vis-a-vis their floors or lack thereof. Expansion about the direct interaction approximation. It is not difficult to pose turbulence problems in which convergence of the orthogonal expansion method is unacceptably slow if it is applied to the power series in time or in strength parameter. Consider, for example, the decay of isotropic turbulence when the initial distribution has all odd order moments 0 and the initial energy is all confined below some wave number k naught. So this is where kind of the Maclaurin analysis is kind of singular because it's only kind of as after the 0th order of things, vis-a-vis the Taylor analysis. So you want, I imagine, trying to figure out how that, where there's a singularity theory as of about the order of the terms and when they're close to unity or close to 0 or anywhere large, then with respect to these kinds of things, is for helping then these moments have as about that the initial energy is all confined below some wave number k naught, or the bounds of the windowing and boxing. The Taylor series in time or strength parameter for the energy in a wave number k greater than 2 to the n k naught. So here also we're looking for like identities in the factorial and exponential, or that's where my mind goes because I have one, and so It has all zero coefficients until order 2n plus 2, while the labor of computing coefficients goes up rapidly with order. So this is kind of in the cases where it's like our finite element analysis is falling out. And so we're having to compute many more terms to get close. And so eventually the nonlinear terms will not vanish, and indeed then trying to figure out what happens here in the middle is the next great thing to try and figure out in terms of the overall analysis in the field, to not just invent a new particular application, but to figure out a way to interpret all the usual derivations and applications insofar as how it could be that then it would be possible to make it so that there would be along the lines of a way to rewrite these same terms, and as with regards to how it could so follow this way. (241). All right, here we go. Well, we're not quite there yet. Assume for simplicity that the initial statistics and the structure of the A's, these matrices, these Phythian Christoffels. So I haven't heard of Phythian yet so much, but it appears he's got some interesting stuff going on. Phythian. I mean, relating it to Christoffel, basically. Assume for simplicity is such that y sub I t, y sub j t prime, the bracket equals 0 for I not equal to j. So this is one of the conditions of orthogonality for the usual sort of terms, their product terms, the parameters, the analysis for all t and t prime, e.g. when the y's are Fourier modes of isotropic turbulence. Then the direct interaction equations are Creighton, 1958, These raw partial terms up front equals these sums up after the box terms in either order of their orientation, where the right-hand rule is and the left-hand rule are two different things, and the right-hand rule is usual orientation. So this takes terms as over both orientations of these formulas in these terms and their reciprocals in the before and after, or the inverse in the inverted terms vis-a-vis these forward functions. Infinitesimals. It's got raw differentials and infinitesimals. And here we formalize that with iota values, and we have a formal fundamental elementary continuous domain theory to equip this sort of turbulence theory. May be thought of as representing a dynamical coupling of an infinite collection of systems, namely all the realizations in the ensemble. However, in contrast to the original direct interaction model, the couplings are non-random. For lambda equals 1 reduces to 6.5 reduces to 6.2, which was as of Phythian, and is an example of being able to solve something for where terms result natural and that where otherwise they don't, because it's not infinity or it's unbounded or this and that. How to figure it out. For lambda equals 0, it is a dynamically linear equation. Since change of any values in a single realization has infinitesimal effect on averages over the infinite ensemble. So this is this 1, 0, and infinity, and that they form an identity. 1 over infinity equals 0, and normally it's like, well, infinity is just not a number, but they are the numbers. Wow. So since changes of any value in a singularization has infinitesimal effect on averages over the infinite ensemble. The direct interaction response function equation follows immediately from 6.5. at lambda equals 0 in view of this from the dynamical linearity. Concluding remarks of convergence to turbulence functions. From the point of view of basic turbulence theory, the principal import of the work reported above is first, the conclusion there is at least one way to construct approximations for statistical functions that are uniformly convergent in time, starting from a specification of the moments of initial probability distribution. Of equal interest is the emergence of conditions which must be satisfied for this to be possible. One condition is the physically obvious requirement that quantity average evolve without any singular behavior in all the realizations of the ensemble. However, we also found that we could prove uniform convergence to the correct function without ambiguity only if the function in question was analytic at t equals 0, a condition which could be assured only by excluding initial distributions that permitted unbounded amplitudes. Unbounded distributions like the Gaussian could be covered by the convergence theory only if they were represented as the limit of a sequence of bounded distributions. The implication is that the familiar diagram expansions, which result from averaging turn by turn over a Gaussian distribution, may actually not determine uniquely the functions they represent. So, paradoxically, our approximation procedure gave excellent convergence when this caution was disregarded. In the sections 3 and 4, we treated series with zero radius of convergence obtained from Gaussian distributions. Then it'd kind of be looking for like other reasons why the models combine, that they have complementary terms. That what we're seeing as 0, or the presence of nothing, is really this fine balance of them. Maybe so. In fact, it could be so. And it's for theory then to extract what are these superclassical features of otherwise these classical models. What you don't see with regards to how that could be so. The accuracy of the results. Bousset's bounds for turbulent shear flow. Max Planck Institute for Physik and Astrophysik, Munich, or München. Bounds on the transport of momentum and turbulent shear flow are derived by variational methods. Numerical methods. Regimes of plane Couette flow, channel flow, and pipe flow are considered. The Euler equations resemble the basic Navier-Stokes equations of motion in many respects and may serve as model equations for turbulence. This book has got quite a lot going on, and it helps explain a lot of these methods. These kinds of things really kind of have a lot going on. Qualitative sketch of the boundary layer region of the vector field yielding maximum transport of momentum. So you got the mean flow, and then it just kind of has, there's a centrality as associated with it. And then there's just kind of a branching of that as down to the regime of basically the surface where its shear layer is, whether that it is the shear layer or it has a shear layer, that being granular to the point is that it's smooth. The turbulent momentum transport is carried predominantly by wall-attached eddies with a streamwise axis. Structure of the minimizing vector field. The thicknesses of subsequent boundary layers differ always by a factor of about 4, which becomes the exact factor in the asymptotic case of mu tending to infinity. So this help explains that this boxing and squaring has what's going on with this kind of thing. Bousset, bounds for turbulent shear flow. The limiting stability property of turbulent shear flow. The similarity, which is found in the comparison, between the observed structure of turbulence and minimizing solution of the variational problem suggests that realized turbulent shear flow represents a flow with maximum momentum transport or with maximum dissipation at a given Reynolds number on all possible solutions of the Navier-Stokes equations of motion. So this kind of statement is a kind of a nice qualitative statement, and it helps establish kind of like a fundamental theorem, and otherwise a theorem of fundamental objects, a theory of fundamental objects. It helps describe a fact as about the objects that can then be used to assign to other models that follow it would have to at least exhibit it, or as other regards that having models with this kind of property satisfy at least having this kind of property. The comparison between the observed structure of turbulence and the minimizing solution of the variational problem suggests that the realized transport turbulent shear flow represents a flow with maximum momentum transport. It's a minimization problem here with respect to that's the quite usual notion of overall constancy and currency. We do not think that this fact indicates the existence of an extremum principle for turbulent flow, which is valid in an exact sense. See, he's letting out that basically we frame that on in terms of this concept of the Solomon-Weinberg's study of the strong nuclear force and what binds atoms together called the strong nuclear force, and that in the middle of the atom, in the core, is asymptotic freedom. So in the extremum, it's not like it's not like a diamond at a coal. It's the opposite. It's a super classical conceptual inverse, which is kind of how it is, and that is as for an extremum principle. The tendency towards the property of maximum momentum transport seems rather to be the consequence of the instability of the laminar sublayer, as the following consideration suggests. A laminar flow usually becomes unstable if the characteristic Reynolds number exceeds a certain critical value Reynolds C. If a criterion of this kind is applied to the laminar sublayer adjacent to the wall in which momentum transport M is carried by viscous stresses, we obtain the real part of delta is on order of being greater than or equal to Reynolds C as the criterion for instability, or towards stability in dynamism, that you have stability in being static and stability in being dynamic. Either way, that stability and instability just reflect its tendencies of change or motion. And here they're qualitative criteria. Here's this paper that we thought to look to today. Let's take a brief look at it. Some preliminary results on the behavior of controlled wave disturbances introduced artificially into turbulent channel flow are reported. Weak plane wave disturbances are introduced by vibrating ribbons near each wall. The amplitude and relative phase of the streamwise component of the induced wave is induced from a hot wire signal, allowing the wave speed and attenuation characteristics and the wave shape to be traced downstream. The normal component and wave Reynolds stresses have been inferred from these data. It appears that Sommerfeld theories attempted to date are inadequate for description of these waves. Wow, casting some shade there on these inadequate wave theories. There is considerable current interest in the possibility of representing shear flow turbulence as a random superposition of appropriate characteristic waves. This is a great idea that constructive interference or destructive interference kind of work together to make it so that superposition results that wave functions add together and make another wave. And that's kind of gets into the whole milieu of all this fungibly sensible. Two distinct but related views have been suggested. In Lumley's 1967 orthogonal decomposition, the waves are effectively marginally stable and strongly coupled through their nonlinear interactions. waves all around. In contrast, Laundal's 1967 wave representation involves waves that are born at some location and decay as they proceed downstream. It's both, right? Laundal's waves might be viewed as the Fourier components of Lumley's characteristic eddies, which, and as we talked about here, that in the Fourier-style analysis, it's like there are infinitely many terms in the expansion, truly. Which representation is the more useful remains to be determined. However, a satisfactory closed equation system for the wave eigenfunctions has not yet been found in either case, and as Laundal suggests, experiments are sorely needed at this point. The primary objective of the present work is the acquisition of appropriate data and the continued development of these ideas. There are two basic ways to approach the experimental problem. One can attempt to deduce the nature of the eigenfunctions from appropriate two-point correlation data. Alternatively, one can seek the same result by systematic controlled perturbations of the basic turbulent shear flows. Indeed, a considerable body of data on the closely related problem of turbulent shear flow or a waving boundary is just becoming available. Kendall, private communication. Stewart, private communication. Such studies treat boundary value problems involving the wave eigenfunctions. Another approach is to introduce a controlled disturbance with a fluid at some point and then study the behavior of the disturbance downstream. This initial value problem leads one directly to decaying eigenmodes of the Laundal type. The present paper describes initial output from just such an experiment. Well, this is a great book. I've been looking forward to reading this for a while because, I don't have a copy of the Journal of Fluid Dynamics around, and I shouldn't avail myself of my local university library if I wanted to get into that in terms of, tier 1 research institutions and stuff like that. So today we kind of talked about, just these usual complementary concepts, complementary duals. That the complementary duals are what help advise us as of this square of opposition, a Fuller dialectic. For synthesis, antithesis, and as after a thesis again. It's complementary duals of a Fuller dialectic. And mathematical model is the same. And then one of the key things talked about today was the natural unit, and 1, 0, and infinity being together a particular set of the least amount of numbers with everything in the middle. Well, good afternoon or good day. I shall so hope that all is well with you and yours these days as the first month of 2024 comes to a close in a while. And what I hope to do is to ponder a bit more how to help affect to relay these considerations in the complementary duals, those that fulfill each other and reflect on each other and perform for their mutual deductive or inductive impasses in their closures and their completions of Fuller deductive closures and their meetings in the middle. That's just the usual paean that I harp on, but it's what's considered the most relevant kind of consideration when all the linear stuff is pretty much run out, and there's it's to be determined that then that still needs to have its complement figured out, because a monoculture is subject entirely to a single disk. So these are the kinds of things. Moment in motion, turbulence theory. 1, 0, and infinity form an expression called the identity expression. They're called the identity expression constants, and 1 over infinity equals 0. But they're algebraic quantities that are as after this establishment of natural units. So long.